Okay, so I'm recording, and you can start whenever you want.
Sure, yeah. So my talk today is going to be on the variational quantum eigensolver and how it can be applied to excited states.
Right.
So there's a couple different things that we could do with understanding excited states, like phase transitions and things like that. And it would just be good to get more knowledge in general on how to simulate quantum systems and the different algorithms that go behind that for quantum computing, and how it can all apply to excited state stuff, because that might be potentially new territory. Starting in, like, I think it's the 1970s or the 1980s, there was a classical algorithm that was developed for finding difficult to exactly solve wave functions. It's called the variational algorithm. And the example you always see in chemistry textbooks when you do quantum chemistry is it applied to helium, because helium's really difficult to exactly solve. But there's an algorithm which can get an approximate solution for it and basically find its ground state energy to pretty high precision. And this is how it works. It's basically, it functions off the principle that any eigenvector you can find, the expectation value of the Hamiltonian on that eigenvector has to be greater than the ground state energy. If this wasn't true, then like for example, if you find a eigenvector which the Hamiltonian, the expectation value of the Hamiltonian is less than the ground state, then that would mean that the energy of that is lower than the ground state, and that would therefore be the ground state. Oh, I think somebody else.
Wait a Okay.
Okay. Okay. Yep. Yeah. So it functions off this principle you can see on the first bullet point, which is that the expectation value of any eigenvector, the Hamiltonian on any eigenvector, has to be greater than or equal to the ground state energy. So what we do is we formulate just an arbitrary random starting eigenvector that's potentially physically motivated. Like we could start with hydrogen orbitals if we're dealing with the helium atom, and we start with that, and we add a couple tunable parameters. And then we classically calculate the expectation value of the energy for that guess at a wave function. And then we can take derivatives of it to try to minimize it. So we end up getting a loss landscape, and we end up finding over time that our potentially bad starting guess will eventually evolve into a better and better actual estimate at the ground state eigenvector and the ground state eigenvalue, which is an estimate of the energy. So basically, we start with an ansatz, just a guess at the wave function, and then we optimize this over time, keep guessing it, and finding what the resulting energy of our better guess is each round. So also, anybody feel free to interrupt me and ask questions if you have any questions during any of this. So. So the potential problem with this is that it is exponentially difficult. So with a growing system size, like imagine you add more and more electrons on, we're going to get the tensor product of all possible orbitals, which means that the complexity of our problem, if we're looking at two orbitals, might be, if we're looking at, two electrons with two orbitals per, it might be 4. And then you add an extra electron, it goes 8. An extra electron, it goes to 16, something like that. So it'll scale exponentially with the larger system size. And this makes it incredibly difficult to do anything but the smallest atoms on classical computers. The good part about this is that quantum systems also have this exact same scaling, where you add one more qubit and your state space doubles. So the idea of simulating quantum systems in a quantum computer is that this exponential growth in the Hilbert space of physical systems is also mirrored in the exponential growth of the Hilbert space in a quantum computer. And the hope is that we can find a way to leverage that to our advantage in order to be able to solve these faster on a quantum computer than is classically possible. So for example, the variational quantum eigensolver, which we'll be talking about a little today, is traditionally used for chemistry problems. It works really well for that stuff, and there's a large body of literature that goes back a few decades, studying different approaches and different methods that you can use on the different chemistry applications. So usually what you do is you use different hydrogen orbitals as your starting guess, and you add them together. So you have your NLMs for people who know quantum mechanics, and your starting wave function guess is a combination of all these different orbitals And what you're doing is you're trying to find the best coefficients for each of these. So you might find that the helium ground state, the first electron you put in, looks a little bit like NLM is 0, and a little bit like it has 0, 1, 0. And then maybe there's some constraints on the angular momentum that might make some of these coefficients 0. And you can also enforce that in your ansatz as well, and you take advantage of that sort of stuff. So yeah, overall, we want to be able to calculate the different energies and eigenvectors, and we start out with initial ansatz, and then we can tune these parameters. And we're also hoping that our quantum system, which scales exponentially as well, might be able to counter the exponential scaling of our physical system. So this brings me to a side note before we get into the variational quantum eigensolver. And this would also be a good time to ask questions if anybody has any questions on the classical variational algorithm. So let me know if you have any questions on that. But if we don't, before I get into the variational quantum eigensolver, I first want to brush over an algorithm called quantum phase estimation. So quantum phase estimation is an incredibly powerful algorithm. It's really common. It's one of the most powerful algorithms there is in quantum computing because it gets an exponential speed up. It involves quantum Fourier transform. That's what this box all the way on the right is. That gate set is a an inverse quantum Fourier transform. And that is exponentially difficult to do on a classical computer, but much, much easier to do on a quantum computer. Which means that if you have a quantum Fourier transform in one of your algorithms, it'll probably run, it's going to get an exponential speed up compared to any classical algorithm. And quantum phase estimation is one such algorithm which has this quantum Fourier transform in it. And the job of quantum phase estimation is to figure out what the phase is of a given eigenvector, psi, on a Hamiltonian H, which we can see. You guys can all see my mouse, right?
Yes.
Yeah. Gotcha. So we have this input state psi, which we prepared beforehand, and we can calculate what the eigenvector is, or the energy expectation value, by applying this algorithm, where we just apply a controlled unitary operator, where this unitary operator is our exponentiated Hamiltonian. And then you can also see one of the important parts is this denominator here gets smaller and smaller as time goes on. So you need exponentially small, fine-tuned unitary operators in order to make this work. And same thing with the quantum Fourier transform. So this is good because it's exponentially fast. It's really strong. It's an incredibly powerful algorithm. But because it needs these exponentially finely tuned gates, it is going to be very sensitive to noise in your system.
Can I just okay, so can you explain this part again? What is this R,
Yes.
the K? We choose those values. I didn't understand the procedure here.
So the idea is quantum phase estimation, the exact math behind it gets a little bit complex, and it would probably need its own talk. If you're interested in learning this more, I can probably do a talk on it, because it's one of the best known algorithms in quantum computing. So it wouldn't be that hard to do a talk on it or find more resources. But essentially, it's probably best at this point to think of it as a black box that finds an eigenvalue. These are all essentially what this does is it does a controlled. This isn't the best diagram to show it, but it does a controlled unitary operator, where the unitary operator is made. It's large on the first one. I think this is actually in reverse order, but it's large on the first.
reverse order.
Yeah, this looks like it's in reverse order. So it's supposed to be large on the first one, and then it gets smaller and smaller and smaller for every qubit that you have. And what that eventually does is it means that it's after you put it through the inverse quantum Fourier transform, it sort of gets let's say the first decimal point of your energy eigenvalue, and then it gets the second decimal point and the third decimal point in binary of all your stuff. So after you pass it through the first decimal point, it gets this because it's essentially, you can think of it as abstractly, this is the largest value. It's not suppressed that much in the denominator, whereas these are suppressed more. So this one, this one does the largest operation it applies the Hamiltonian the most, and therefore it finds the first decimal point of your eigenvalue. These ones are more finely tuned, and they find the smaller and smaller decimal points, so farther and farther back.
Okay, so can I start from like, so we start with a certain eigenstate, but
Yep.
we know that this is an eigenstate of a certain Hamiltonian. We don't know it yet. We just started with a vector and we are trying to find we know that this is an eigenstate of a certain Hamiltonian. Or do we know the Hamiltonian?
Yeah. So you can there are a couple different ways you can do it. It finds the eigenvalue of whatever input state you put in. So the input state you give it could be not a eigenvalue. I forget if after measurement it collapses into an eigenvalue or not. That would be good to look up. I forget about that stuff, but regardless, a way that you could use this to do estimation of ground states is you could try to minimize the expectation value of the eigenvalue, which you find over here, by changing parameters in the psi that you input. So you could give it sort of a dirty wave function and then do gradient descent or other optimization methods to clean it and find the energy, the ground state. And you can do it exponentially faster than any classical algorithm can.
Okay, so we start with a certain vector, which is not necessarily the eigenstate of the Hamiltonian, and we are using it to find one of the eigenvalues of this Hamiltonian, probably the ground state or any. Okay, fine.
If you minimize it, you'll find the ground state because there's a unique ground state, and if you find the smallest value, it has to be there.
Okay.
So.
There are some details for me to learn. Okay, good.
Yeah, no, absolutely. Thanks for asking questions. Yeah, absolutely. So this algorithm is exponentially fast. It's really strong. It's incredibly powerful, but it's really sensitive to noise. And what being sensitive to noise means is until we can make our errors exponentially small through quantum error correction, we won't be able to implement this algorithm. Our modern computers are going to be too noisy to implement this algorithm because it needs these really finely tuned gates. Which brings us to modern, what's usually called NISQ alternatives. It's near-term intermediate scale quantum computers, NISQ algorithms. One of which is the variational quantum eigensolver, which would follow a similar sort of trend to this, but it's a lot more resistant to noise. The trade-off is basically it's more resistant to noise at the cost of being more complex. So this will need an exponential time to run, but we might be able to get polynomial advantage. So we might be able to make it run in square root time or cube root time or something like that, compared to the normal. We won't be able to make it run exponentially faster, which would be a complete game changer, like quantum phase estimation could. But on near-term quantum computers, we might still be able to make it run like square root time, which would be a pretty big speed up. And it would be able to essentially, you could think of it as if you're able to make this algorithms run in square root time, you could access twice the number of qubits. So if we could make our molecules twice as big in chemistry applications, you could think of it roughly as that. And we can simulate those potentially on a quantum computer, which could not be done on a classical computer. So the variational quantum eigensolver is a hybrid quantum classical algorithm. What that means is that the classical side of it, your normal, just imagine you have a laptop hooked up to a quantum computer. The classical side of it does a lot of the heavy lifting that could be error prone. So your classical side of it, classical computers barely ever have any errors. They have the probability of an error is something like 10 to the negative 27, I believe, something like that per gate. So it's incredibly unlikely that your classical algorithm will ever screw up. Versus current quantum algorithms, they have error rates on their 2 qubit gates that are usually at like 10 to the negative 3 for current computers. So the idea is we use the quantum side of it to access the exponentially large Hilbert space, and we use the classical side of it to as soon as we get that, take it out of the quantum system so it doesn't collect errors, and then do all the hard calculations after we took advantage of the exponentially large space, do all those calculations in a classical computer instead. And it works exactly like it works similar to the classical algorithm that I showed you 2 slides ago, where we use the sort of expectation value of the Hamiltonian over different guesses at the ground state wave function in order to calculate the ground state energy. Some potential problems are that you could find local minima, which is why I put this graphic over here. Depending on how you set your parameters up, you could accidentally go into a local minima that's not the true global minima. This is sort of like optimizing a loss function in artificial intelligence, if you think of it that way. So you have to be careful about sort of local minimas, which, I mean, they have to have they would have a good guess at the ground state energy, but it might not be a perfect guess. And if you get stuck in a local minima, you could end up getting a incorrect guess at the perfect at the ground state wave function as well, which might be a problem for calculating excited states, because for certain algorithms, you have to have a good guess at what the ground state wave function is in order to be able to remove that from the system and calculate the excited states, which we can get to in a little bit. But essentially, yeah. So the variational quantum eigensolver is a hybrid algorithm. We calculate as a summary, we calculate the exponentially large Hilbert space in our quantum computer to take advantage of that. When we read it out, we then use that stuff and immediately put it into a classical computer so it's not noisy anymore. And we do all of the other hard calculations in our classical computer before we have to take advantage of our exponentially large Hilbert space again. And then we update our parameters. Is that clear? Yeah, everybody good?
Yeah.
Cool, perfect. So let's take a look at the quantum part, which is the interesting part. So what we want to get from this quantum part is we want to estimate parts of our Hamiltonian. We're essentially, we can break up our Hamiltonian, pretend this O is a Hamiltonian here. It's going to be the operator we're trying to measure our expectation value on. We can break up our Hamiltonian into potentially different parts. For quantum chemistry applications, it almost always looks like this, where you have sort of a harmonic oscillator and then slightly coupled states. So this is like electron-electron repulsion in this term, and this is like the just normal attraction to the nucleus approximated as a simple harmonic oscillator here. What we want to do is we want to calculate each term of this separately, and then we want to add them all together to get an estimate of the energy in a classical computer. So we want to calculate the estimation of this term in our quantum computer, and an estimation of the expectation value of this term in our quantum computer, and then add them together with their corresponding coefficients in a classical computer. So it's not error prone. And we can end up tuning our input wave function, and which we find the expectation value of this over. We can tune that using our classical algorithms as well. So the quantum computer is only used to find the expectation values of these parts and these parts.
Cameron,
yeah, sure.
Are these fermionic creation and annihilation operator?
Yep. Yeah. So in quantum chemistry, they almost always are. I'll get to that in a second. How we deal with fermionic stuff, which that's a very important question. So nice question. Because the commutator algebra is very different for that stuff than it is for bosons. So yeah, good question. But we'll get to that, I think, in the next slide. Once we have our Hamiltonian, what we do in the quantum variational eigensolver is we break our Hamiltonian up into a sequence of polystrings that we're going to measure. So we can basically translate this A dagger A here into a set of polystrings, and then we're going to want to measure the expectation value of these polystrings P, which correspond to our Hamiltonian, and there's also a coefficient because your polystrings have to basically be like between 0 and 1. What if your energy is like 3 or something? So there's a coefficient, and then there's these polystrings P, and we want to measure these polystrings as an expectation value of these over our fine-tuned wave function. That's supposed to be an approximation of our ground state. Just to reiterate again, we have our overall Hamiltonian that looks something like this. We break it up into a series of polystrings, and then we calculate we formulate our guess at a wave function psi of theta, where theta is a tunable parameter. And then we find the expectation value of these polystrings, or the expectation of these individual parts of our Hamiltonian. You can think of it as. And then the expectation value of that. And then we add them all back together with their coefficients again in a classical computer to get an expectation value of our energy. That might be a little bit complex. So I'll leave a second for any questions or you guys to think about this if you'd like. Yeah, this part here.
In the measurement, Cameron, what do you mean? Like this measurement 0 P dagger U 0? It means that you have evolved. Yes.
Yeah. So U is going to be the operator that creates our starting state. So we always start with a vacuum state in quantum field, in quantum computing. So the vacuum state is the all zeros string. We have to formulate our guess at a wave function out of that. So we have to apply some operator, an operator U, that takes it from the ground state, the just starting all zero state, and turns it into our guess at the actual state. That's what U does. So we do that, and actually I think it might be missing a U dagger on the other side, but
yeah,
basically, yeah, that's a typo. That's my bad. It's missing a U dagger on the side.
Okay, that's it. Because I was surprised because there was like something was missing there. That's okay then.
Yeah, no, all good. No. Thanks for catching that. Good job. But yeah, so you want to you attached to the ground state or to the all zero string makes our psi. Yeah, exactly. Yes, and then we apply our P, and then we apply our U dagger, which then turns it back into the all zero string, which we can measure. And that's how we get our expectation values. So we basically just measure all these poly strings and measure the expectation values of all these poly strings over in our quantum computer, using these U's, U daggers, and the P poly strings. So good question. Nice catch. Okay, cool. And the quantum part is this sort of like expectation value of P over psi. And then the classical part is summing it all back up with its corresponding coefficients. So this part is able to take advantage of the exponentially large Hilbert space to do it fast. And then this part is able to take advantage of the sort of error resilience of classical computers to just not screw it up. We can go into the next part, which is fermionic systems. Nice job. Fermionic systems. So usually quantum chemistry applications are all about electron structure. And electrons are fermionic particles, which means that we need to be able to have fermionic commutator algebra, which is actually anti-commutators. We have to have whatever operators we represent A and A dagger as. They have to be anti-commuting. Normal polygates don't do this, which means that we have to give it a new encoding. This new encoding, the most two popular ones are the Jordan-Wigner encoding and the Bravi-Kitaev encoding, if I'm pronouncing that right. The exact specifics of this are a little bit complicated, but basically you just try to formulate a anti-commuting operator from polygates. So you make a polygate that anti-commutes for this other set of polygates, and then you have this sort of finite fermionic space that you can work in after that. And you do all of your measurements and everything using that encoding. It's basically just a way to translate our normal quantum computer, which uses polygates, into fermionic operators. Cool. So if we're interested in quantum chaotic systems, it depends on whether or not this is important, depends on whether or not we want to do sort of fermionic systems or bosonic systems. If we want to do something that's fermionic, we're probably going to have to use these encodings as well. And there's active research in this area on finding more efficient encodings, because these encodings can be somewhat expensive to employ. This is an active area of research as well for potentially better ways to encode these fermionic operators.
Cameron, but later we'll talk about this. We can do this for bosonic systems to study the excited state quantum phase transitions first in bosonic systems.
Sure, absolutely, yeah. And that might be a much better approach because it might require less gates on a near-term quantum computer, which will make it a lot less error-prone. So you'll get a lot better results if you stick to bosonic systems, possibly. I'll have to look more into that to see exactly how you do simulations that way, but I think it'll work out a lot better if we stick to bosonic systems for the start, especially with our near-term noisy computers. Cool. So any questions up to this point on anything so far? We're about to go into excited state variational quantum eigensolver. So if you have any questions about the normal variational quantum eigensolver or anything related to that, let me know now, because we're going to go into the excited state stuff. Okay, cool. So if we don't have any questions about that, we can go to the next one. This is a paper which went out on the archive pretty recently. From what I've seen, excited states variational quantum eigensolver algorithms, working with excited states is a fairly active topic up to this point. If you look on the left-hand side, you can see that this was put on the archive on May 8th of this year, so it's like 4 months ago. Almost all of the papers that I read over the last couple weeks and getting ready for this presentation as well were put out on the archive within the last like 3 or 4 months. So this is a very active area of research. And it's something that we might be able to, if we could find some contributions in quantum chaos, it would probably have a lot of stuff to stand on at this moment. So there's, very active. It's good stuff.
Let's upload this paper in our Dropbox, okay?
Yep, absolutely. I have a couple papers, like I think 3 or 4 papers, which I'm planning on uploading to the Dropbox, which deal with excited state variational algorithms. And I found one on phase transitions as well in a Kagome lattice, which I think might be interesting because it found that I can get to that later, but I can get to it now. There's a paper which tried to use the variational quantum eigensolver to find the ground state of a Kagome lattice. I think that's how you pronounce it. It's the frustrated state one. And what they found was that near a phase transition point, the variational quantum eigensolver by itself didn't perform that well because it got confused on whether or not it was supposed to be finding the ground state or the excited state near the phase transition point. If you knew previously that this is more on the ground state side of one of them, you could use your ansatz and put your starting state as say that you have like temperature changing or magnetic field changing. You can use a previously determined ground state at a lower magnetic field to find the ground state at a higher magnetic field, and they found that helped find phase transitions. And because the algorithm would perform poorly without that starting ansatz of a previously found ground state. So that's just something interesting that we should keep in mind if we were trying to do something with ground states. I'll upload that to the Dropbox if anybody's interested. So yeah, but back to the variational quantum eigensolver. This is the algorithm that I'm going to be looking at the most closely, which is the folded spectrum VQE. It has some problems because well, I'll get to that in a second, but it's potentially more costly in certain systems computationally. But it's a really easy way to show how the variational quantum eigensolver algorithm can be adapted to excited states. So how do we fold the spectrum? The normal variational quantum eigensolver just tries to find the expectation value of the Hamiltonian, right? That just finds the energy. And it tries to minimize the expectation value of the Hamiltonian to find the state that corresponds to it. What you can do to find excited states is instead you find the expectation value of your Hamiltonian, but you subtract off just some sort of scalar number quantity to focus on the region that would have energies like this. So for example, if we want something at 5 eV, we could do the Hamiltonian minus a scalar value, all diagonal matrix of 5s. And that would end up subtracting 5 from all of it. Like you see over here, it finds our energies minus 5. And then we do that squared, and it would give us a parabola that would look like this, sort of. And by minimizing this, we find the eigenvectors and eigenvalues and all the states that correspond to the closest eigenvalues and eigenvectors to 5 eV. For example, if you wanted to do this with like the hydrogen atom, you could just do the Hamiltonian of the hydrogen atom and then vary omega, increase it each time. So try it as 1, 2, 3, 4, 5, and then see the states that you get out and the eigenvalues you get out. And at some point, the ground state is going to be so small that omega overpowers it, and it's no longer the ground state in this system because omega sort of excites it. And now the new true ground state by folding the spectrum is one of the excited states. So does that make sense? We're subtracting off this new quantity and squaring it in order to change what the sort of ground state seems to be in our system. Cool. So the benefit is that it's really obvious. It's nice and easy to see mathematically that this would sort of focus on, if we minimize it, focus on excited states, excited eigenvalues and excited eigenvectors and all of that. But the bad part is that this part is squared. So by it being squared, that means that we'd have to, on average, measure a squared number of polystrings from a few slides ago. The number of p alphas here is going to square, potentially. In many systems, it will square. And what that means is that our computation is going to be, a squared as difficult. If it would have taken us 10 seconds before, it could take us 100 seconds now. You can think of it that way, which means that since the variational quantum eigensolver only gets a polynomial speedup, if it only gets a quadratic speedup in some systems, and this algorithm gets a quadratic speed, like slow down, it's going to completely cancel it out. And we have to be careful of whether or not we're going to actually get some sort of an advantage by using a quantum computer if we use this algorithm or not. In the paper that was shown previously, which I'll go back to here, folded spectrum VQE, this is for specifically molecular excited states. And they did it for molecular excited states because they have a very specific structure. They have this sort of structure, the O operator here, and they found a way to get around this squared scaling by using the anti-commutator algebra to cancel out a bunch of them. So they basically got rid of a bunch of the p alphas that you need by anti-commuting their operators through. And because of that, they were able to get it away from that quadratic scaling, and they're able to show a quantum advantage from it. So that's something we have to think of. It depends on the being able to get that quadratic speed up depends exactly on the structure of the system in question for this algorithm. So if we want to use this for chaotic quantum systems, it might only work for a certain class of chaotic systems that have specific structure. That's a sort of general idea that I got out of the paper that paper that I just showed, is that you need a specific structure in order to get good quantum scaling from this and get a speed up. And if we want to apply it to certain chaotic systems, it might be constrained by that. Yeah, that's for using the variational quantum eigensolver for it. So keep that in mind. However, since this technique gets a potentially like quadratic slowdown, since quantum phase estimation, which we mentioned previously, gets an exponential speed up, it could still work to get advantage in the fault tolerant regime, a decade or two from now, when we have quantum phase estimation, because it would get an exponential speed up, which completely destroys the quadratic slowdown that it would get. So, this is still nice to know. It's a nice algorithm to see, and I think it's there's a lot of algorithms that you can use to do excited state quantum phase variational quantum algorithms, and this is the most straightforward I've seen, so it makes the best introduction in my opinion, and the technique would still work for quantum phase estimation years down the line. So yeah, that's this is a good example of how it's possible, and one of the approaches that people have taken towards finding excited states, eigenvectors and eigenvalues, and determining the spectrum and everything. But there's a lot of others as well. So we have a lot of other possible variational quantum eigensolver excited state algorithms. These algorithms have been explored a lot lately. I've seen all of the papers that I've read have really been in the last 3 or 4 months. So this is a very active area of research for sort of finding excited states in quantum computers. One of them, the top one you see here, the variational quantum deflation algorithm, follows a classical algorithm that's similar to the one for helium that I showed earlier. So for helium, how you want to find the excited state is classically speaking, is you want to find the ground state first, and then make sure that all future states are orthogonal to the ground state that you found, which basically just prevents you from finding any more of the ground state. It takes the ground state completely out of the next state you find, and then you minimize it again to find the first excited state. The variational quantum deflation algorithm works very, very similarly. It's the exact same thing, but in a quantum computer, where you find your ground state, which here in this equation over here would be psi j of theta. So you could think of it as psi 0 of theta. And what this is this is the ground state that was previously determined by a run. So you have to run this algorithm once to get the ground state, and then you find that ground state psi, and then you alter the Hamiltonian to make it not energetically favorable anymore. You make this beta j incredibly high so that the energy of the ground state is now just made gigantic. And now when you minimize it the second time, it can't find that original ground state because the energy of it is giant, so it won't minimize it. And instead, it's forced to find the first excited state. And once we find the first excited state, we can also alter the Hamiltonian again and sort of build up our entire spectrum that way. by making each state that we find, each next state that we find and categorize, we make that unfavorable by making it have a higher energy. And that's how the variational quantum deflation algorithm works. It's one of the most popular algorithms. It's more popular than the previous one I showed, the folded algorithm. It's one of the most popular algorithms because it's been well studied in classical systems as well through classical computers. But it has some problems to it. The problems are that any error in the earlier states are going to affect the later states. So if we guess wrong what the ground state is, or if we, like I said earlier, get stuck in a local minima of what the ground state is, we choose this one rather than this one by accident through our variational algorithm, then that's going to end up screwing up all excited states as well, because we're going to be making it orthogonal to the wrong thing. So any of that, and so any miscalculations in the earlier steps or any noise in the earlier steps that makes us guess slightly wrong is going to be propagated to the next layers. And that makes the variational quantum deflation algorithm, it's still noise resilient, but it's less noise resilient. And finding excited states is going to be more and more difficult the more excited the state is. So the higher energy level the state is, the less certain this algorithm is going to find it. And the worse its guesses are going to be on the energy and the actual state itself. So that's one of the most popular ones. There's also the subspace search variational quantum eigensolver algorithm, which I haven't dove into too deeply, but it's from what I've read, it seems to be the second favorite of the fields right now. Although, this is a rapidly evolving field, so maybe I'm wrong about that. Maybe it changed last week, who knows? But this one, basically, it finds a way, from what I've read, and I don't know too much about this one, so I wouldn't be able to answer too many questions. But from what I've read, it seems to identify the lowest subspace and calculate the lowest subspace all at the same time. So you're able to find like the lowest 5 energy eigenstates and enforce orthogonality to all of those and just find all 5 of those immediately. And then if you want to find more, you just change it so it has a different K. That's what I've read so far. But if you're interested in potentially implementing that, I'd go do a more thorough search. And I have some resources at the end of this that you could take a look at as well. And one of the other popular ones is the quantum subspace expansion, where you basically start out by finding the ground state, and then you know enough about the system to apply excitation operators. Essentially, you need to find something that's similar to a ladder operator so you can excite the state over and over again. And then after you find the ground state, you kind of know everything else in the spectrum because you already have that operator. And you just use a quantum system to calculate it faster. So those are other excited state variational quantum eigensolver algorithms that I've found. So yeah, let me know if you have any questions on those.
No, this okay. So yeah, so this is what I was going to ask, the papers. No, so then I think we have to read and then find out which one would be, I don't know, or we can try them all and see which one works better for our problem.
Sure, yeah, absolutely. Yeah, so on here I have a couple different papers. I have the original variational quantum eigensolver paper, which I think was proposed in 2017, I want to say, which adapted the normal classical variational algorithm to a quantum computer. I also have the folded VQE, which I just presented on and showed on a slide a couple slides ago. And I have one that shows how you can parallelize VQEs for excited states, as well as using variational quantum eigensolver for the ground state in phase transitions. So these are the different papers I read in preparation for this talk. Yeah, a really good introduction, if you'd like to read this, is the folded VQE paper, because not only does it show the folded VQE algorithm, but it also does a pretty good introduction of the variational quantum eigensolver algorithm just in its base. So the original one, it gives a pretty good introduction to the field of the variational quantum eigensolver. Oh, I can't talk today. It does a pretty good introduction to the field, and then it also shows you how to do it for excited states. So I recommend that paper first, and then going on to other papers or looking at the citations in those to see all the other sort of modern papers in the field that have been used to do excited state investigations.
Very good.
Cool.
Okay.
Yep. So that's everything I have. Let me know if you have any questions. So
I'll stop recording.